In this lecture, again, thinking about combinational logic, we're going to look at the ways in which concatenation, that is simply combining bits together, can be a helpful utility in Verilog code. And notice the core lesson here is just using curly brackets means glue bits together. In this example, we're taking the unsaturated sum and appending or representing that with the carry bit on top and the unsaturated sum as the bottom 8 bits of the resulting 9-bit number. So let's spend a minute, think through that, and take a look at what we've got. As always, whenever we have numbers and add them together, it produces an extra bit. And let's think for a minute about some of the options of what we can do with that extra bit. For example, let's think about adding two numbers. We have a 4-bit number we're calling A, a 4-bit number we're calling B. The top value is A, the bottom value here is B. We're going to add them together and place them in a 4-bit value C, and you can see the operation in Verilog here. C is equal to A plus B. So of course what that produces is a 4-bit sum, and of course we would get the expected value over here. We would just add these together. This would produce a 0, and we'll add a carry up here at the top just to make this arithmetic a little bit clearer. And we'll continue to just do our typical binary arithmetic thing. So we would end up with a sum of 1. Notice in Verilog, when we tell Verilog that what we want is a 4-bit result to two 4-bit add-ins or things that we're going to add, A and B, it does give us the bottom and only the bottom 4 bits here in C. What we've obviously discarded here is that there is a carry out of this last bit, but we didn't really have anywhere to put that carry, and I'll just represent it for right now right here, even though we didn't have a place to put that carry. So we have a couple options. One option is I can make C a little bit bigger. So if C becomes a 5-bit number, that means we now have room for that carry, and so it becomes appended to the top of the result, and now we have a result that makes a bit more numeric sense. We're adding 10 plus 7, and now we do get the number 17, 1 in the 16th position plus a 1 in the 1's position for a total of 17. However, sometimes we want to very clearly separate the carry that we get from the actual result that we get, and that's where concatenation can be a very handy methodology. So what we've done here is declare an additional 1-bit variable. By default, of course, in Verilog, values are 1-bit if I don't otherwise declare it. And then we've reduced our variable C to just be a 4-bit result. So we have this 5-bit answer that's produced by the sum. So you could, thinking about it this way, we've taken carry out and C, and we're assigning that to our 5-bit result that we're seeing right here. And of course what Verilog will do is very conveniently split that into two pieces so that our carry out bit will take the highest bit. Of course that's the 1 right here, so that'll just be a single bit value, then the bit 1, and then C, which is our sum, will be that 4-bit value that we've been looking at earlier, 0001, and I'll represent that in the proper Verilog syntax. So again, what concatenation does as an output, in other words, we're saying the output or the result of A plus B should be split into a 1-bit result at the top plus a 4-bit result at the bottom. And again, those are all specified by specifying the sizes, a 3-bit and by default a 1-bit here for carry out. And those get split up nicely. So concatenation is a great way in this case to split up that result. Again, you can see very clearly we have an 8-bit unsaturated sum, and notice that both of our inputs are also 8-bit values right here. And we're splitting that into the 1-bit carry, and then of course our 8-bit result here. What we'd like to do is take a look at the value. Typically, if you add 255 plus 1 in 8-bit arithmetic, the answer is 0, which doesn't make a lot of sense unless you're taking that carry into account or otherwise recognizing. So an option is, rather than produce a result of 0, which is completely incorrect, perhaps we should just produce a result of 255, which is at least not as bad. That's what saturating arithmetic does. So all we have to do is look at that carry bit. If we saw a carry, it means we went past 255, so we'll simply place the value 255 in our sum. If there's no carry, then we just stick with the sum that we already had. And again, concatenation provides a convenient way to express taking 9 bits and breaking that into smaller pieces. In our previous exercise, we noticed that another way that concatenation was used. Here in the encoder, we took a 5-bit value, row and column decoded. Here I'm representing it nicely, and split that and created that. These bottom 3 bits come from call decoded. And of course, the top 2 bits come from the row value that's passed into this function, and it combines those two to create a single 5-bit value, and then we can write our case statement on those 5-bit values, 0, 0 for the row, in this case 0, 0, 1 for the column decoded value, and combine that together in a single simplified value. Remember, as always, to spend some time and work through each of these exercises rather than searching the internet for a result or allowing an LLM to dictate it. This should be relatively straightforward exercises. Again, all we're doing, as you saw in the video, is splitting things into a 4-bit sum and a 1-bit cout. Of course, that's short for carry out. And based on the video, that should be a very direct result for you. After you've mastered this example, and again, we're using concatenation, those curly brackets, to perform that assignment, let's take a look at something which requires a bit more thought. Here again, we have code that's going to be very similar to what was done in the lecture material. We have 2 8-bit values, A and B, and we can simply use a conditional operator to decide whether we're producing a saturating sum or a non-saturating sum. So again, this is a minor modification of the code. I would suggest introducing an intermediate value to hold the possibly saturated sum, and then the solution becomes fairly straightforward. Finally, let's look at a barrel shifter. Briefly, for some background, we're going to take some value, in this case an 8-bit value, and talk about how that looks like when it's shifted and rotated around. So again, we have this value. Let me correct that Verilog syntax. We have some value and we'd like to shift it. In this example you see, we're shifting it by a total of 4 bits. So here we go. We're ready to shift right by those 4 bits, but notice this is not simply a shift, but we're going to rotate those bits around. In other words, we're not discarding them, but we're moving them from the bottom of the number to the top. So let's think about what happens. For example, when we shift 1 time, this bit goes away and is moved back to the top. So that so far we've shifted by 1 bit. Here's our 2nd bit shift, our 3rd bit shift, or perhaps I should say bit rotate, and our 4th bit rotate. So notice what happened. We've taken these bottom 4 bits and now put them at the top of the number. The top 4 bits have been shifted down so that they're at the bottom of the number. So there's a shift rotate going on in this barrel shifter. What a barrel shifter means is I have freedom to specify how far to shift. It's not a constant shift or 1 or 2 bits, but I can specify anywhere between a 0 and a 7-bit movement. And that's part of what makes a barrel shifter a bit more complex. So in terms of implementing this, think about what we're asking. For each of these different shifts, you can put in a case statement. Since we're doing a case statement, the first piece is always to put it inside a procedural block and always begin end. Before the case statement, the first thing to do is assign a valid value to the output. I'm actually going to assign the output right back to the input, right? A is our input value, Y is the output value after it's being shifted, and AMT, or amount, is how far we're going to shift it. So of course we're going to take a look at the amount, and decide how far we're going to shift it. Don't forget when writing a case statement to always terminate it properly with that end case value. And now we'll start out by looking at a small shift and move our way up to a larger shift. So if we're shifting, for example, by just 1 bit, and notice I can freely use decimal values here. Verilog understands that amount is a 3-bit value, so that means I can look at values between 0 and 7. Notice I deliberately did not write the case for 0. In fact, this handles when my shift is 0, y is equal to a, so that's not really necessary for me to cover this. Now think about it. When we're shifting that 1-bit value, let's go back and think about how that shift works. What we're doing, of course, is simply moving our value from one side of the number. We're moving a single bit here and placing it over here. So in Verilog, I can think about the value that I have as composed of 2 pieces. So we'll think about it as the top 7 bits that get shifted down by 1, and the bottom bit, which will be rotated around back to the top. Let's go ahead and just create that number that we're intending to make, and then talk about how to build that. So again, here's the number that we'll start with for our shift. And in this case, for the code that we're writing, we're going to write a shift of 1. And that means we take this topmost bit and stick it here. And I'm going to kind of space things out a little bit to make that a bit more obvious. And I'll also put an underscore here. Again, we're thinking of the number in 2 chunks. A top chunk that gets moved down by 1, and the bottom bit that gets rotated to the top. So if I were to write this first number in Verilog syntax using our nice concatenation syntax, and again remember that this number is the variable a, then I can simply write that as a combination, right? If I want to talk about the top bits of a, that would be bits 7 to 1. Now originally we had something that looked like this, right? We took the top 7 bits of a and the bottom bit of a and rearranged it. This is the way they were at the beginning before the shift happened. After the shift happens, we're actually putting the bottom bit at the top and the top 7 bits at the bottom. So our output simply, therefore, is y, of course, is our output. The output is composed of the bottommost bit followed by the next 7 bits. And that is exactly what we can put down for our case statement. And of course, we need to complete that for the rest of the possibilities for this barrel shift operation. In our final video, let's think a little bit more about signed arithmetic and how that plays into writing additional Verilog code.